Well, hello everybody and welcome back. In this video we're going to start Unit 6 of AP Calculus, Integration and Accumulation of Change. We're going to start with Section 6.1, which is all about exploring accumulations of change. And the lesson here opens with a lot of text, so let's kind of see what I have to say. It says, through the first several units of the year, our focus was on the derivative and its role as a rate of change. We were frequently given a function and then asked to determine the rate of change by using the derivative. So that really was our first 5 units. With this unit, that's going to begin to change. We're going to, instead of exploring and focusing on change, we're going to begin looking at accumulation of change. Okay? So what's going to happen now is instead of starting with a function and finding a rate of change from it, we're going to start with a rate of change and figure out information about the original function. And the way we do that is by accumulating that rate of change through the use of area, actually. One of the most natural places for us to begin looking at this comes from particle motion. A while back we talked about how if we have a position function, the derivative of that position function is the velocity, and the derivative of the velocity is the acceleration, etc., etc. Now if we start with the velocity, we can determine information about the position from the velocity by using the accumulation of change. So let's start with our first example. Mr. Thomas drives his RV across Interstate 80 at a constant velocity of 55 miles per hour. If he drives 2 hours and 15 minutes, how far did he go? Okay, so looking at this problem, and unfortunately my picture got a little bit blurry here, but right here we have a line representing the 55 miles per hour that I'm driving. And over here, we have another line representing the 2.25 hours that I'm driving, 2 hours and 15 minutes, or 2.25 hours. So if I want to find the total distance that was traveled by the RV in this time, I'm going to accumulate that rate of change. I'm going to accumulate all of this area underneath the curve between time 0 and time 2.25. Now, of course, if you look at that, you see that's a rectangle, and finding the area of a rectangle is something that should be fairly simple for all of us. We're just going to go ahead and find the area of the rectangle by taking the length times the width. We take 55 times 2.25. And when we're done calculating that, we find that the total distance that was traveled was 123.75 miles. And so that's how we accumulate our change. We're just going to find the area underneath the curve between the left boundary and the right boundary is the accumulation of the change. Let's look at example 2. This one's a little trickier because our time unit along the bottom does not match our speed unit along the top here. I do have to point out a few points here because, like I said, my graph did not transfer over very well. This is the point 0, 55, and this, of course, is our speed in miles per hour along the vertical axis. And over here, I have the point 8, 15. And along the bottom here is our time, and our time is measured in seconds. It doesn't take me 8 hours to slow down to a speed of 15 miles per hour. It takes me 8 seconds, which presents an interesting concept for us here. But first we're going to go straight forward with my calculation. I want to go ahead and accumulate all of this area. And in order to do that, I'm going to take use some area formula. I can split this up into a rectangle and a triangle. I can just treat it like a trapezoid the whole time. But what happens here is I have, let's go ahead and do a trapezoid. I've got 1/2 times the average of the bases, which is 55 plus 15, and those are measured in miles per hour, times the height of the trapezoid, which is this distance right here, which is 8, and that is measured in seconds. So if I do all of this calculation, let's see, I've got 1/2 times 70 times 8. That gives me 280. But if I multiplied these units out, I've got miles per hour times seconds. And if I want to know how far I traveled along the off-ramp, I want to convert this over to just miles. So I've got to get rid of the seconds per hour here. And of course, the way we do that, since we've got miles times seconds per hour, I'm going to multiply by an expression representing hours per second. In 1 hour, there are 3,600 seconds. I'm going to go ahead and multiply by that, and when I do that, that gives me my final distance traveled in miles. And so I take 280 times 1 over 3,600. (280) times 1 over 3,600, and that's 7/90ths of a mile was the distance that I traveled down that off-ramp. Okay, all right, let's continue on here. Example 3, the graph below represents the rate at which water is leaking out of a storage tank. The appropriate units are given on the graph. How much water has leaked out of the tank after 9 minutes? So in those 9 minutes, we've got all of this area underneath here that we're accumulating to represent how much was spilled. And so now all I need to do is calculate what that actual area was. And for me, I'm going to break this up into 3 parts. Rectangle right here, semicircle right here, and this triangle right here, and go ahead and calculate all of those values. So we've got the rectangle is 6 by 2. We've got a semicircle, which is 1/2 times pi times the radius squared, since it's half a circle. And I've got a triangle with a base of 3 and a height of 2. And now I'm just going to go ahead and calculate all these values. That's 12 plus 2 pi plus, looks like 3. And so I get 15 plus 2 pi. And since this is gallons per minute times minutes, this is going to be measured in gallons. And if I wanted to, I could convert that over to a decimal. And I already punched this up on my calculator. It's 21.283 gallons. All right. And so that's how we accumulate the change to figure out the total amount of water that has leaked out of the storage tank. We accumulate all the area underneath the curve. All right, last example from this lesson. A particle is moving along the x-axis with a velocity modeled by r of t and shown in the graph below. How far is the particle from its starting position after 2 seconds? So that means we want to go from time 0 to time 2. And the area underneath the curve there is 1/2 times the base, which is 2, times the height, which is 10. So that's going to be equal to 10 centimeters. And so the particle is 10 centimeters to the right. All right. All right. Part B, how far is the particle from its position at time 2 after time 8 seconds? So notice where this is different from any of the ones we've done so far is the area here is underneath the axis, which means that when we accumulate this area, we're accumulating negative area that is below the axis. So what I'm going to do is I'm going to calculate all of that. I've got a triangle with a base of 3 and a height of 15. I've got a rectangle with a width of 2 and a height of 15. And I've got a triangle with a base of 1 and a height of 15. And I add all of those together and I get 60, but it's 60 below. So typically we would calculate this and all of this would be negative 60, which in this interpretation, since the particle's moving along the x-axis, this is going to be 60 units, I have my units, 60 centimeters to the left. So the negative area represents motion to the left instead of motion to the right. And then our last part, how far is the particle from its starting position after 10 seconds? So remember, it went 10 centimeters to the right in part A, and it goes 60 centimeters to the left in part B. And now from 8 to 10, it goes 1/2 times 2 times 10. And so when we do all of this calculation, we end up with -40, which means that after 10 seconds, the particle is 40 centimeters to the left of its starting position. All right, and so that's how we can use accumulations of use area to find the accumulation of change of a function. And that's what this entire unit is built around. All right, that brings us to the end of this video. Go ahead and do your practice problems, and we'll see you next time for section 6.2, which is approximating areas with Riemann sums. All right, have a great rest of your day, everybody. See you next time.